All looks good on YouTube.
Fabulous. Thank you, Will. Well, good evening, everyone in Zoom and on YouTube, and welcome to this March presentation by the Astronomical Society of Edinburgh. I'm Neil Martin, and I'll do a short intro before I hand over to our guest speaker this evening, Dr. Susan Cartwright. So we'll start off with some news, and I'll cover some of the events that are happening in the near future. And then, as I say, I'll hand over to Dr. Cartwright for this evening's presentation. So coming soon, in fact, a week tomorrow, the partial solar eclipse. And we hope to be streaming this event, weather permitting, using our Cook telescope at Calton Hill. We'll also be live with some members and some equipment at the same location. So either join us online or in person, and let's hope for some clear skies. In terms of timing, the eclipse is scheduled to begin. The eclipse will happen at just after 8 minutes past 10 on Saturday morning. The moon will be taking the biggest slice out of the sun just after 5 past 11, and then the event finishes just after 5 past 12. And if you want to know what this looks like, here's some pictures of the fun that we had the last time this happened, and we all got together on the Calton Hill back in October 22. Beyond that event, we have our next in-person meeting on the 4th of April at Augustine Church, and that's a members night, and I believe there are still some slots available. So if you've got a topic you'd like to share with the rest of us, then please let Nigel know, and we'll get that added to the schedule. The following Wednesday, the 9th of April, we have our usual imaging and observing group session. That's online for members only, and these are becoming action-packed and full of content. So yeah, please do come along if you have an interest in either imaging or observing. Our mid-month topic next month is to be confirmed, but we do have a guest speaker lined up, Dr. Sarah Hurst. So look forward to hearing what Sarah's going to talk to us about. But for this evening, we have a talk which has a very engaging title. I'm very much looking forward to this. And so without further ado, I will hand the microphone over to Dr. Susan Cartwright for her talk. So Susan, over to you.
Okay, so thanks for the invitation. And as advertised, my intention is to talk about neutrinos and the mystery of the missing antimatter. So in order to set the scene for this talk, the first thing that I have to explain is what is antimatter, for those who've only heard of it as the power source of the Starship Enterprise. So the standard model of elementary particles contains this array of fundamental particles. The ones in purple are the quarks, up, down, charm, strange, top and bottom. The ones in light blue are the charged leptons, and the ones in green are my favorite particles, the neutrinos. And the ones that we are familiar with are this first set here, which are the lightest ones. They are the ones that are most stable, and the up and down quarks in different combinations make up protons and neutrons, and we're all familiar with the electron. The neutrinos are kind of the silent members of this family. They don't do very much, but they're very numerous, and as I hope to show in this talk, they may be very important for our existence. But for every one of these 12 particles, there is in fact a corresponding antiparticle with opposite quantum numbers. So, for example, the antiparticle of the electron is the positron, which has the same mass but opposite charge. And there are similar antiparticles for every particle in the Standard Model. So that is antimatter. So the next question, that's what antimatter is. Why does my title claim that there is some antimatter is missing? Well, if you consider particle physics experiments such as the ATLAS experiment at the Large Hadron Collider at CERN, thanks to Einstein's E equals mc squared, the protons that collide in the Large Hadron Collider and are accelerated to very high energies, by E equals mc squared, that energy can be converted into mass. So you can collide two protons together and make very much heavier particles, such as particles containing top quarks. But you always get particle-antiparticle pairs when you do that. If you make a top quark, you also make an anti-top antiquark. If you make an electron, you make a positron as well. And that contrasts with the situation when we look out at our universe, because in the universe, we see a great deal of matter. All of these objects that you see in this deep field image are made of matter. We see very little antimatter. So the question is, if when we create matter, we always get particle-antiparticle pairs, what happened to all the antiparticles? The first question that you should ask is, how do I know that all of those things in the Hubble deep field are made of matter? Well, we know that within our galaxy there is very little antimatter, because we can observe cosmic rays, which are particles from outer space, and very few of them are antiparticles. And the number of antiparticles we can get can be well explained by recognizing that we can make antimatter on Earth in particle accelerators, and there are natural particle accelerators out in space. The highest energy cosmic rays have far higher energies than the protons in the Large Hadron Collider, and those high energy particles can smash into other particles and make particle-antiparticle pairs, just like they do in the LHC. So the galaxy is made of matter. Could there be anti-galaxies out in the distant cosmos somewhere? Well, not really. Firstly, there's no mechanism by which you could somehow segregate the matter and the antimatter by megaparsecs, but also because, as we all know, matter and antimatter annihilate when they meet, and they produce characteristic energy gamma rays. If you have a positron and an electron, they annihilate to produce two gamma rays, each of which has an energy that is equivalent to the mass of the electron, so 511 kiloelectron volts. And if you've ever had a PET scan in a hospital, that's how they work. The test isotope that you're injected with, or which you swallow, contains a radioisotope that emits positrons, and what is imaged is the gamma rays produced when that positron annihilates with an electron in your tissues. And so if there were anti-galaxies out there, you'd expect to see these characteristic gamma rays coming from empty space when the anti-cosmic rays from these other galaxies hit intergalactic gas in between the galaxies and annihilated. So we don't see that. Also, we can measure the abundance of the light elements, the heavy isotope of hydrogen, known as deuterium. That's this D/H line here. Helium and lithium, all of which are made in the first few minutes after the Big Bang. And the key point here is that by comparing the measurements, which are the yellow bars, with the theoretical predictions, which are the colored lines, we can measure the ratio of baryons to photons. That is to say, baryons is particle physics speak for protons and neutrons. And if you measure the baryon to photon ratio in particle physics events like those at the Large Hadron Collider, you find that the ratio of charged particles to photons is about 1:1. Roughly speaking, you get one charged particle for every photon. In the universe, as you can see from the best fit lines, which are these hashed lines here, the ratio is about 1 to 1.7 billion. So what that suggests is that matter and antimatter were indeed produced in the Big Bang, or in the very early universe, and most of the antimatter and the matter did indeed annihilate, as we would expect, but somehow there was one proton left over for every 1.7 billion annihilations. And this is the mystery of the missing antimatter. Why? We can understand why some things might have got left over, because as the density of the particles and antiparticles gets less as they annihilate, eventually they'll be too far away from each other for there to be a meaningful chance that they will collide. But there's no reason why that should preferentially happen to the matter. We would still expect a 50-50 mix of matter and antimatter, even if diluted by the annihilations, and this we do not see. So this is one of the fundamental questions in cosmology, is how, assuming that particle physics in the early universe behaved like particle physics now, did we manage to wind up with this great asymmetry between the matter and antimatter content of the universe? So the question is, do we have to bake that asymmetry into the Big Bang somehow, or can we generate it in the early universe, even if the Big Bang itself was, as you would expect, symmetrical, just like the LHC, and was making particle-antiparticle pairs? And we have known since the 1970s that this can actually be done, and the conditions under which you can generate such an asymmetry were first laid out by the Russian theoretical physicist Andrei Sakharov, who's nowadays, insofar as he's remembered at all, is remembered more as a dissident against the Soviet system. But he was a very distinguished theoretical physicist, and he derived these three conditions that you have to satisfy in order to generate the universe we see from a symmetrical initial state. So the first of these is fairly obvious. There must be interactions which violate baryon number conservation. In all the interactions that we observe in experiments like ATLAS, the number of baryons, which is essentially the number of quarks minus the number of antiquarks, or if you prefer, the number of protons minus the number of antiprotons, is always conserved. So if you have a proton in the final state, you have some baryon, not necessarily a proton, it could, for example, be a neutron, but you have to have some baryon in the final state. And so if you start off with a total baryon number of 0, in other words, your number of protons is equal to your number of antiprotons, or your number of quarks is equal to your number of antiquarks, then if that were true in the early universe, you would always end up with a symmetry between matter and antimatter, because if the baryon number is conserved, you can't start out with B equals 0 and end up with B greater than 0. So that's one condition which self-evidently has to be satisfied. The second condition is that the interactions must take place out of thermal equilibrium. Thermal equilibrium is the state that things settle down to if they're left undisturbed for a period of time. And the reason it's called an equilibrium is that in equilibrium, there is no net flow in any particular direction. And in particular, the number of forward reactions is equal to the number of reverse reactions. And clearly, if we had some hypothetical reaction that created a proton, shall we say, the reverse reaction would destroy a proton, and we wouldn't end up, and if the rate of forward and reverse reactions was equal, then we wouldn't gain anything. So obviously, you need your interactions to be taking place under conditions which are not in equilibrium, and where you can therefore have an excess of forward reactions over reverse reactions. The third one is a bit more esoteric. Sakharov showed that these interactions must also violate a symmetry which has the not entirely transparent name of CP. CP stands for charge parity, which probably makes you no wiser. So let's investigate what CP symmetry means, because this is where neutrinos are going to come into the picture. So C is the operation by which you take all the particles in a reaction and you convert them to antiparticles. C stands for charge conjugation, because the most visible result of converting a particle to an antiparticle is that its charge is reversed. So as we saw earlier, an electron becomes a positron. If your reaction is symmetric under C, that means that the reaction involving antiparticles would behave in exactly the same way as the reaction that involves particles. Clearly, if all operations are symmetric under C, we're not going to get anywhere, because if that were the case, our hypothetical baryon creating reaction would be matched by an identical antibaryon creating anti-reaction, and we would be no further forward. We'd still be creating equal numbers of baryons and antibaryons. P stands for parity, and parity is the operation of reversing all directions and velocities. So it's a sort of 3D mirror reflection. And again, if something is symmetric under P, it means that if you look at it in the mirror, you still get a valid reaction. And that is commonly true. For example, if you were to take, since I'm in Sheffield, I will of course use snooker as an example. If you were to take a video of a snooker match and you were to mirror reflect the table, then provided you were well into the match, and so you didn't get a clue from where the bought colours are, you wouldn't be able to tell that I'd done that. The behaviour of the balls would be exactly the same in the mirror as it would be in the crucible. Most everyday processes do conserve P symmetry. CP is then the combination of C and P. You convert all your particles into antiparticles and reflect the whole thing in the mirror. Now, the point here is that we actually know that weak interactions do violate C symmetry and they do violate P symmetry. But CP symmetry can be conserved even if C and P are individually not conserved. And if this were so, it would be bad news, because if C were violated, you'd have a baryon creating reaction, and if C were not violated, rather, you would have a baryon creating reaction matched by an antibaryon creating anti-reaction. If C is violated but CP is conserved, our baryon creating reaction is cancelled out by a mirror reversed antibaryon creating anti-reaction. And since the universe doesn't care which direction its particles are going in, that would still be sufficient to prevent us from winding up with a universe in which matter dominates over antimatter. To give you a feeling for how this works, I have here an analogy which I will freely confess I stole from a chap called Jonas Radebacher, who I think is now at Bristol. He was interviewing for a fellowship, and I was on the selection panel, and he presented this in his fellowship application talk. And when he walked out the room, all the particle physicists on the panel looked at each other and said, "I'm stealing that." So here it is. Thanks, Jonas. So let's take it that this is our original reaction. This is an Escher etching, which I think is called day and night. If we invert the color scheme in a suitable graphics package, that's analogous to converting all our particles into antiparticles, and we get this picture, which is clearly different from that one. So this etching does not conserve C. It looks, the antiparticles look different from the particles. If I reflect my picture in a mirror, I get this. This also looks different from my original picture. So with this etching, both C and P are not symmetric. The picture does not look the same if I convert black to white, and it does not look the same if I reflect it in a mirror. But if I do both those things, then I wind up with a picture that looks very much like my original picture. So although it isn't symmetric under C and it isn't symmetric under P, it is very nearly symmetric under CP. It isn't quite symmetrical. If you look closely, you can see that this little train of barges, which was in the White River in the original, is in the Black River on the CP reversed one. And that's actually quite appropriate for our analogy, because in fact, in the weak interaction, we do know that although that C and P are very strongly violated, and CP is almost but not quite conserved. So can we satisfy the Sakharov conditions in the early universe? Can we move from a symmetrical initial state to a universe like we have today, where there is lots of matter and very little antimatter? So here are our conditions again. there must be interactions which violate baryon number conservation. Now, I said to you that we have never seen such a reaction in the 100 years or so that we've been doing particle physics. However, surprisingly, in the standard model theory, this is actually okay. There are known processes. I am not a theorist, so please don't ask me any about details about these. They're known as sphalerons, which do violate baryon number conservation, but only at extremely high energies. So we don't see them today because we are not in a high energy universe anymore. But in the very early universe, a tiny fraction of a second after the Big Bang, these things would be operating and you would be able to violate baryon number conservation. So there are such interactions. Do they take place out of thermal equilibrium? Well, yes, this shouldn't be a problem. Thermal equilibrium, as its name suggests, note the thermal here, it occurs when everything has settled down to a stable temperature. But at early times, the universe is expanding very, very fast. And as it expands, it cools. So it is not difficult to have reactions out of thermal equilibrium. In fact, it is normal for reactions in the early universe to be out of thermal equilibrium. So those two conditions we would expect would be met in the early universe. So the question is, to CP or not to CP? That is the question. And this is where neutrinos come in. The first thing to say is that CP symmetry is not violated in the strong interactions that occur between quarks and hold up and down quarks together in the proton, and also hold protons together in the atomic nucleus, nor is it violated in the electromagnetic interaction, electricity and magnetism. Why it's not violated in the strong interaction is a very good question. In fact, there is no fundamental property of the mathematics of the standard model that would prevent the strong interaction from violating CP symmetry, but experimentally it does not do so. There are theories as to why that should be the case, but that's actually a completely different talk. If you haven't already had him give a talk, my colleague Ed Dorr would give you a talk on axions, which are a consequence of a theory that is designed to understand why CP symmetry is conserved in the strong interaction. In the weak interaction, things are different. The weak interaction violates charge conjugation, a reaction that has certain properties under particles doesn't necessarily have the same properties in antiparticles. And it also violates parity. And it almost conserves the combined operation, but as long ago as 1964, so 60 years ago, CP violation was discovered in weak interactions of quarks. And it's been studied extensively ever since. One of the experiments at Large Hadron Collider, LHCb, is designed specifically to look at processes like this. However, it has been studied extensively. We know by how much CP is violated in quark interactions. It is not enough to explain the matter-antimatter asymmetry we see in the universe. And it's not enough by several orders of magnitude. We're not talking about a factor of 2 here. We're talking about a factor of tens of thousands. So we need an additional source of CP violation to explain the amount by which matter in our universe dominates over antimatter. So if it doesn't work in the weak interactions of quarks, our best hope is to look for CP violation in the lepton sector, that is CP violation in neutrino interactions. This would lead to violation of lepton number conservation rather than baryon number conservation, but sphalerons, these interactions that occur in very high energies and violate baryon number conservation, it turns out also violate lepton number conservation. What they conserve is the difference between those two. So if you have reactions that will generate non-zero lepton number, you can parlay that into generating non-zero baryon number. And this theory is called leptogenesis, so production of the matter-antimatter asymmetry through the leptons. How does this work? Here we need to divert into quantum mechanics. As I said on my first slide, I have 3 green circles for 3 types of neutrino. And these are known as nu e, nu mu, and nu tau, and they partner with the corresponding charged particles. So nu e is the neutrino counterpart of the electron, nu mu is the neutrino counterpart of the muon, which is a particle like the electron, but about 200 times more massive. And nu tau is the neutrino partner of the tau lepton, which is more massive still, and about twice as massive as the proton. And these are known in particle physics as flavors. And something that was not in the original standard model, where it was assumed that all of these particles were precisely massless, just like photons, is that we now know that neutrinos also come in 3 different mass states, imaginatively known as nu1, nu2, and nu3. The key point is that these labels do not match up. You cannot assign a specific mass to, for example, nu mu. You cannot assign a specific flavor to mass state nu1. They are quantum mechanical mixed states. And so they are, so this is essentially very much like Schrodinger's cat. Schrodinger's, we all know about Schrodinger's cat. You put a cat in a box, you have within the box a mechanism which, depending on the decay of a radioactive atom, which is random, will or will not release poison gas to kill off the cat. Until you open the box, you do not know the state of your cat. And in quantum mechanics, your cat is both dead and alive. If you produce a neutrino in association with an electron so that you know it is an electron neutrino, you do not know what its mass is. If you could open the box, which sadly you can't because neutrinos are so weakly interacting that measuring one specific neutrino is basically impossible. But if you could open the box, you could observe any one of these 3 masses with a probability that we can calculate, but you wouldn't know in advance which you would measure. Only the probability that you would measure what nu1, nu2, or nu3. And key point here is that another feature of quantum mechanics is that it says that free particles behave like waves. And if you consider our electron neutrino, it is a mixture of three different masses, and those three different masses correspond to different wavelengths. So if you allow your neutrino to travel for a long distance, waves that started out in phase will get out of phase because a distance that is 100 wavelengths of mass 1 might be only 95 wavelengths of mass 2 and 89.5 wavelengths of mass 3, for example. So you would wind up with a different mixture of the three masses than you had when you started, and therefore your neutrino, because it is now a different mixture of masses, is no longer a pure electron neutrino. It has now become a mixture of different neutrinos, and therefore you can produce a neutrino as an electron neutrino or a muon neutrino, allow it to travel for some distance, and you will see it interact as a different type of neutrino, because as it travels, the different mass states get out of alignment. It is rather amusing to realize that Lederman, Steinberger, and Schwartz got a Nobel Prize in physics for apparently proving that this didn't happen. And the reason for that was simply that because neutrinos are very, very weakly interacting, it's very hard to get enough neutrinos into your detector to get a decent signal. So in the 1960s, everybody, of course, stuffed their detector as close to their source of neutrinos as they could get it, and therefore they didn't give the mass states time to get out of phase, and so they always observed the same type of neutrino that they started with. If they'd put their detector further away, they wouldn't have got the same answer. The mathematics of neutrino oscillation is this horrible matrix equation. I do not expect you all to be familiar with matrix mathematics, so do not worry about this. The key point is that this term in blue is the term that produces the CP violation. And experimentally, the signature of this, the experimental evidence that this quantity is not just 1, in other words, that delta is not 0, is a difference between the oscillations of neutrinos and the oscillations of antineutrinos. So you look at your oscillation signal, you look at how it behaves with neutrinos, you look at how it behaves with antineutrinos, and if they are the same, then you have no evidence for violation of CP symmetry. But if they are different, then you do have evidence for the violation of CP symmetry. So in order to do that, we need to compare oscillation results for neutrinos and antineutrinos. And this is where experimentalists like me come in. You need to make a neutrino beam, and ideally, you need to also be able to make an antineutrino beam. Fortunately, we know how to do this. The first thing you do is build a high-intensity proton accelerator. This one shows the one we use, which is at a facility on the east coast of Japan called J-Park. High-intensity proton accelerators are expensive. Fortunately, if you are a neutrino physicist, you can use one that belongs to somebody else. I don't believe there is any neutrino experiment that has ever existed that has built its own proton beam. And this particular one is actually was built as a proton source to do nuclear physics with. So the next thing you do, having got your proton accelerator, is to extract the proton beam and smash it into a target. So this picture here is a blow up of this bit of that picture. Here are your protons. You bring them out here, and you have a target station, which is here. I might add that anybody who knows anything about accelerators could immediately see from this diagram that this was an afterthought. This was not baked into the design of this accelerator from the start. And you can tell that because our beam comes off the inside of the proton ring. Nobody in their right mind extracts beams off the inside of the ring, because in order to make particles go around in a circle like this rather than going off in a straight line, you have to use magnets to bend the trajectory. And so the easy thing to do to extract a beam is to turn off a magnet and let it go straight on. So sensible beam extractions off the outside of the ring. If you try to take it off the inside, you have to have a kicker magnet that is higher strength to bend it more, and that is clearly more difficult and more expensive. The fact that we had to do it shows that the design of the ring was already more or less finalized when somebody in the Japanese science ministry said, hang on, we can do a neutrino experiment with this proton ring. So having extracted your beam and smashed it into a target, when high energy protons hit a target, you get lots and lots of unstable particles called pions, and pions very helpfully decay into muons and muon neutrinos. If they are positively charged pions, you get neutrinos. If they are negatively charged pions, you get antineutrinos. So you use a magnetic field after the target. These are the so-called horns, to select out either your positively charged particle pions or your negatively charged pions, and then you direct the ones you want down this tunnel and allow them to decay. The lifetime of a pion is only on average 26 nanoseconds, so they decay quite fast, and then you have everything else gets absorbed by the material between this tunnel and your detector, which is out here, and the only thing that isn't absorbed is the neutrinos. So that's how you make a neutrino beam. And the really good thing about this technique is that just by changing the direction in which your current is running in your three electromagnets here, you can switch from focusing pi pluses and getting neutrinos to focusing pi minuses and getting antineutrinos. So this is a perfect setup for studying CP violation, because you can produce either a neutrino beam or an antineutrino beam and direct it at the same experiment. In contrast, for example, nuclear reactors are excellent sources of neutrinos, but they produce only antineutrinos. They don't produce neutrinos. Conversely, the sun is also a source of neutrinos, but it produces only neutrinos. It does not produce antineutrinos. Or if you make your neutrinos using an accelerator, you can flip from a neutrino beam to an antineutrino beam literally with the flick of a switch. So you can make a neutrino beam. Next question, how do you detect the neutrinos that you make? First thing to note is that most of the time you don't. The weak interaction is called that for a reason. Mostly your neutrinos will annoyingly pass through your detector, leaving absolutely no trace. For example, if you look at your thumbnail, approximately 65 billion neutrinos from the sun are passing through your thumbnail every second. The fact that the sun has now set does not make a difference because they will pass through the Earth as well. And you don't need to worry about those 65 billion neutrinos because through is the operative word. They go through you, through the Earth, out into outer space, and they don't notice that anything has happened. So the only way that you can do neutrino physics is by having very intense sources so that the very tiny chance that something will interact will happen often enough that you will get a usable sample. It's a bit like the lottery. If I buy a lottery ticket, the chances of my obtaining, what was it for the Euro billion, 66 million or something, are so tiny that that the chances that I will drop dead before the draw are a great deal higher. But nonetheless, that jackpot will almost certainly be won because a lot of people buy tickets. And the same is true with neutrino physics. The chances that a specific neutrino will interact in your detector are absolutely minute. But if you have a sufficiently intense beam, the chance that some neutrinos will interact is high enough to give you an experiment that will produce usable results. So the most important kind of interaction from our point of view, looking at for evidence of neutrino oscillation, is the kind in which the neutrino converts to its partner lepton. So if this is an electron neutrino, it will convert to an electron. If it's a muon neutrino, it will convert to a muon. And the reason that these are the ones we want is that the kind of charged particle you get, electron, muon, or tau, tells you what kind of neutrino interacted. And the charge, positive or negative, of that particle tells you whether it was a neutrino or an antineutrino. So muon neutrinos will produce negative muons, electron antineutrinos will produce positrons, and so on. And this allows us to study the way in which neutrinos change flavor after they have traveled a certain distance. This is the experiment I work on. It's called T2K for Tokai to Kamioka, and it's a fairly typical neutrino experiment. So here is our neutrino beam being made on the east coast of Japan. And after about 280 meters from the target that the protons smash into, there is a detector that looks at the beam when it has traveled too short a distance for anything to have changed. It then travels across Japan, a distance of just under 300 kilometers, and it then encounters the Super Kamiokande experiment under a mountain in the west of Japan. This is Super K. It's a cylinder of pure water. This photograph was taken when it had been emptied for maintenance. It's usually full of water. It's about 40 meters in diameter and about 40 meters high. Here you see three people on a platform checking these things here, which are photomultiplier tubes, which are very sensitive light detectors. And the reason it's very large is that the other thing you do to get a usable neutrino sample, firstly, you have an intense beam, and secondly, you have the largest detector you can possibly build. And if we extract from from that horrible matrix equation the bit that's got the CP violating factor in it, it turns out that this bit of the equation governs the oscillation in which muon neutrinos convert to electron neutrinos. So our beam is almost entirely muon neutrinos. So what we need to do is to see if any of them have converted to electron neutrinos, and we recognize that by identifying electrons rather than muons in our detector. And so you do that with a muon neutrino beam, then you flip the magnet currents and you do it again for an antineutrino beam. And the question is whether the properties of the oscillation are the same for neutrinos as they are for antineutrinos. So how do we measure this? Well, Super K is basically a very large water tank, and I do mean very large. The total mass of water in Super K is about 50,000 tons. We only use about half of that for analysis because we discard events near the edges because they are more likely to be background. Key point here is that although nothing can travel faster than the speed of light in a vacuum, when light enters a transparent material such as water or glass, it is slowed down by the refractive index of that material. So light in water travels at about 3/4 of the speed of light in a vacuum. Charged particles are not slowed down by the refractive index. So a charged particle can be traveling faster than the speed of light in water. For example, if your particle is traveling at 99% of the speed of light, which is perfectly legal, and it goes through a water tank, it is still traveling at 99% of the speed of light, but the photons have slowed down to 75% of the speed of light. And the effect of this is very much like the effect of a plane traveling faster than the speed of sound. If a plane travels faster than the speed of sound, you get a sonic boom. If a charged particle travels faster than the speed of light in a transparent medium, you get a sort of optical boom, a cone of light, which is known as Cherenkov radiation after a Czech physicist called Pavel Cherenkov, who was one of the early people who studied this effect. So the idea is that your neutrino enters the tank, it interacts with a water molecule, it converts to a muon or an electron, and that muon or electron produces a cone of blue light, which you detect using the photomultiplier tubes that line the walls of our water tank. So both muons and electrons will do this, but electrons are much lighter than muons. So as they travel through the water, they tend to scatter, tend to be bounced about by the other water molecules. And the result of that is that you get a fuzzy cone. So when it hits the side of the detector, you get a ring, but it's fuzzy. It has there's light detected outside the main ring. Whereas a muon, being much heavier, isn't so easily knocked off course, goes in a nice straight line, and you get a nice sharp ring. And so we have devised computer programs that quantify the degree of fuzziness. And you can see that in the simulations, the green here is muons, the orange is electrons, and this degree of fuzziness indicator here, you can see in the simulations, it cleanly separates muons from electrons, and the points with error bars are the data, and you can see that there is clear evidence that there are indeed electron-like events in our data sample. So we do get oscillation where a beam that started off as almost entirely muon neutrinos interacts in super K with a significant proportion of electron-like interactions. That's how it works in Cherenkov experiments. There are other styles of neutrino experiment. For example, NOVA in the USA uses liquid scintillator rather than relying on Cherenkov light. And it can also tell muons from electrons. It uses a different method, but it still works. Muons and electrons are, by particle physics standards, really quite easy particles to tell apart, which is a good thing from the point of view of this kind of experiment. So that is the beginner's guide to neutrino experiments. What do we get? Well, the most recent analysis is actually a joint analysis with the NOVA experiment. It's important to do this kind of joint analysis because it helps to reduce experiment-dependent systematic errors. And in fact, our individual analysis and NOVAs don't really agree all that well, so it's a good thing to cooperate and see if we can understand that. And this is the result we get. So this is the plots here essentially show the probability of that particular value of this quantity delta. The ones with the red squares over them, 0 and pi, represent CP symmetry being observed, so no difference between neutrinos and antineutrinos. Anything else represents violation of CP symmetry. And you can see that there are two curves here. The reason for that is that for technical reasons, we do not know which of our mass states is the lightest. We know that the mass of state 2 is greater than the mass of state 1, but we do not know whether state 3 is the heaviest of the three or the lightest of the three. If it's the heaviest, that's known as normal mass ordering. If it's the lightest, that's known as inverted mass ordering. And you can see that if inverted mass ordering is correct, then there is a very strong preference for CP violation in this analysis. If normal mass ordering is correct, the situation is not as clear. And this is not really terribly surprising because in the individual analyses, NOVA's results agreed with theta k's for inverted ordering, but the two experiments did not agree for normal ordering. So when you try to combine them, because they prefer different answers, you wind up with a much broader distribution, which certainly doesn't like plus pi over 2, but anything from 0 to minus pi is perfectly okay. So at the moment, none of this is sufficiently definitive to count as a discovery in particle physics. Particle physicists are very fussy about the statistical significance of discoveries, and this does not come close to reaching the threshold to claim a discovery. And we don't know whether normal or inverted mass ordering is correct. So at the moment, it's a result, but it's not a result that actually tells you anything. So what is the future of this? Can we answer the question of why the universe is made of matter and not a 50-50 mix of matter and antimatter? Well, both theta k and NOVA are still collecting data. So we will get better statistics, and we will hopefully improve our understanding of the data that we have so that we can make better analyses. But Also, over the next few years, there's a whole new generation of neutrino experiments that are due to start. The Juno experiment in China is almost ready. It's due to begin taking data this year. It's a reactor experiment. It can't measure CP violation itself because reactor experiments are not sensitive to CP violation. But what it can do is tell us whether the mass ordering of neutrino mass states is the normal ordering or the inverted ordering. And then we can all stop having to draw two curves on all our graphs. We can pick one of them and stick to it. That would be good. Super Kamiokande is being replaced by a new and bigger water tank called Hyper Kamiokande, which rather than being 40 meters in diameter and 40 meters high, is 70 meters in diameter and 70 meters high. That's a very big hole. And it is under construction and due to start taking data in 2028. And there is also Dune, which is in the USA, and it is a different technology using liquid argon, and it should start taking data around about 2030 or so, if it doesn't get canned by Trump, which is not something at the moment that anybody is putting money on. And these will, Hyper-K and Dune are both capable of giving a fairly definite answer to the question of whether CP violation is or is not present. This is a simulation for Dune, and the different shades of green and yellow show different assumptions about the value of this CP violating phase. And you can see that that these are really give quite different results. And so within a few years of running, we should definitely be able to measure this parameter. So to summarize, our universe is made of matter. And that is something that seems natural to us because it's our universe and we're used to it. But it's actually quite surprising that it is not a 50-50 mix of matter and antimatter. That's what we get when we make particles in experiments. There's no obvious reason why that wouldn't be what we got in the universe. It is theoretically possible to generate this excess of matter from an initial state which behaves like our particle interactions in accelerators if we satisfy the Sakharov conditions. The hardest one to meet is the need to violate CP symmetry. And although it's been known for 60 years that CP symmetry is violated in particles that are made of quarks, the amount of CP violation in that sector is nowhere near enough to explain the excess of matter over antimatter that we see in our universe. So the question is, can neutrinos do the job? At the moment, the jury is still out. But the next generation of neutrino experiments, which are much larger and have more intense beams, should be able to reach a verdict. And therefore, it is at least possible that in maybe 10 years' time, we will know whether neutrinos hold the answer to the mystery of the missing antimatter. So thanks for listening. And do you have any questions?
Well, thank you very much, Dr. Cartwright. What always amazes me is how hard we have to work and are continuing to work to explain the universe around us, and you know, your talk covered that in great detail. So thank you very much, everyone. Can we come off mute and thank Dr. Cartwright? And now we'll turn to questions from the Zoom audience. Does anyone have any questions? If you pop them in chat or raise your hand, we can come to you.
I've got a question, Neil, if that's okay.
Absolutely,
Yep.
John, go for it.
Thanks for the talk, Dr. Cartwright. I may have missed a bit in your talk. I guess you're looking for the difference in oscillations between neutrinos and antineutrinos
That's
to
right,
show
yes.
the violation. But it seems to me that from the initial state when they're generated to the point where they're detected, there's no charge there's no charge change. So the violation must be in symmetry, in parity. But what's the difference there that you're looking for that indicates that there's a violation?
Yeah, the key point is that this quantity here, if you work through the horrendous matrix multiplication, which I honestly do not recommend, the result is about 5 lines long. It's one of those things where you very carefully code it into your computer program, and then you try very hard not to think about it anymore. But the key point is that this means that this behaves differently, the sign changes for neutrinos and antineutrinos, which means that the probability that you measure a muon neutrino converting to an electron neutrino, if this quantity is different, if delta is different from 0 or pi, will actually give you a different probability for starting from a neutrino, from a muon neutrino, or starting from a muon antineutrino. So it's indirect. It's not directly looking, doing a CP transformation and seeing if you get the same answer, but this is the manifestation of CP violation in oscillation, and what it does is modify the oscillation probabilities.
Okay, thank you.
Any more questions from the Zoom audience?
Yes, I'd like to ask a question if I can, Neil, please.
Fire away, Nigel.
Thank you. Great talk. Thank you very much, Dr. Cartwright. I just wondered, you mentioned that the new experiments that are coming online in the next few years, the American one was using a different technology, using liquefied argon, I think you mentioned.
Yep.
How are they expecting that to improve the detection of neutrinos over purified?
When you use liquid argon, you are measuring you detect using a different method. What happens is that your neutrino interacts with the argon, and this causes both. Liquid argon is a scintillator, so it responds to a disturbance if you hit your atom and it recoils. It responds to that recoil by emitting light, so you get a scintillation signal, but it also responds by producing ionization. So it ionizes argon atoms, and you stick an electric field around your liquid argon volume, and you drift those electrons to one side and collect them. And this gives you a much cleaner measurement of the track than a Cherenkov light signal. And it also is sensitive to particles that are moving too slowly to generate Cherenkov radiation. So the event reconstruction in a liquid argon detector is much more complete than it is in a water Cherenkov experiment. The downside is that you don't get as much mass because you have to keep your argon liquid. I mean, argon under normal room temperature is a gas, and you want it to be liquid, so you have to wrap your tank in a cryostat to keep it cold, and that limits the size of the detector you can build. Hypercamiocande will have a fiducial mass, that is to say, avoiding the edges, the mass of water you actually use for events that you analyze, of 187,000 tons. You cannot make a liquid argon detector that big. You can't keep it at the same temperature, and argon is only liquid over a fairly small temperature range, so if you're not careful, you freeze it in some places and have it boiling in other places, which would be very bad. Dune will have, if it ever gets completely built, 4 separate detectors, each of them with a mass of only 10 kilotons. So it's much smaller than Hyper-K. And what you are basically doing is a trade-off between events, each of which gives you much more information because they're much more clean, much more detailed in what they record, but fewer events because you have a lower mass. I should say it's very good to have 2 very different detectors doing the same physics, because it reduces the chance of false alarms, because if 2 experiments that are using completely different methods to reconstruct their events get the same answer, you can be pretty sure they've got the right answer.
It's a real event. Yes, that's great. Thank you very much.
Thanks, Nigel. Any more questions for Dr. Cartwright? Okay, Will, do we have any questions from the YouTube audience?
Yes, we do. We have one from AC in Southern California, sunny, from what I gather on the chat. And basically, what happened to all the energy that was generated when the initial matter and antimatter in the universe annihilated?
Basically, it's still here, and we called it the cosmic microwave background. Because the universe expands, as it expands, it cools. So photons that started life as gamma rays are now a black body spectrum at 3 Kelvin. But yeah, the energy didn't vaporize, it just got spread out and cooled as the universe expands.
Marvelous. Thank you very much. Excellent talk. Thank you.
No more questions from the YouTube audience, Will?
No more.
Okay, fantastic. Well, let's bring the evening to a close by again thanking Dr. Cartwright for her talk in the usual way. Thank you very much indeed, Dr. Cartwright.
Well, thank you for the invitation, and I hope people enjoyed the talk.
Yeah, very much so. And to everyone else, thanks for attending this evening, and we'll see you all on Saturday the 29th for the solar eclipse.
Thank you.
Thanks
Good
and
night.
good night.
Bye. Good night.
Thank
Bye.
you. Bye.
Right, thank you.
Good night.
Bye.